Welcome to TechNation. Today we make quantum mechanics look as easy as turning on a light switch. Today, we're going to delve into one of the most mind-bending concepts in quantum physics, quantum entanglement, and the EPR paradox. But wait, before you start scratching your head, we promise to make it so easy to understand that even your pet goldfish can grasp the idea. So buckle up, because as we dive into this topic, we'll reveal some astonishing details that will make you question everything you know about the world around you. Trust us, you don't want to miss out on what's to come. So sit tight, stay till the end of the video, and prepare to have your mind blown. Quantum entanglement is the phenomenon where two or more particles become linked in such a way that their properties are interdependent, regardless of the distance between them. The implications of this concept are far-reaching, with potential applications in quantum computing, cryptography, and teleportation. One of the most intriguing consequences of quantum entanglement is the EPR paradox, which was first proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. The paradox challenges our understanding of the principles of quantum mechanics and suggests that the theory may be incomplete. At the heart of the EPR paradox is the idea that entangled particles are connected in a way that cannot be explained by classical physics. The paradox has been the subject of much debate and experimentation over the years and continues to be an active area of research today. In this video, we'll explore the fascinating world of quantum entanglement and the EPR paradox. We'll delve into the latest research on entanglement and its potential applications in technology and society. We'll also reveal some astonishing details that will challenge your understanding of the universe and the nature of reality. So stay tuned and get ready to have your mind blown as we explore the fascinating world of quantum entanglement and the EPR paradox. The concept of entanglement is difficult to understand because it defies our classical intuition. In classical mechanics, objects are either in one state or another, and there is no inherent connection between them. However, in quantum mechanics, particles can exist in multiple states at the same time, and their properties are intertwined in ways that we do not yet fully understand. One of the most common examples of quantum entanglement is the entanglement of spin states. In quantum mechanics, spin is a fundamental property of particles that describes the intrinsic angular momentum of the particle. Imagine two particles, A and B, that are entangled with respect to their spin states. If you measure the spin of particle A, you will find that it is either up or down. However, the state of particle B will also be determined, and it will be the opposite of particle A. This means that if particle A is measured to be up, then particle B will be measured to be down, and vice versa. Quantum entanglement is a critical component of quantum computing because it allows for the creation of quantum bits or qubits, which are the building blocks of quantum computers. In classical computing, bits are either 0 or 1, but in quantum computing, qubits can exist in a superposition of both states simultaneously. Entanglement allows for the manipulation of multiple qubits at the same time, which is essential for performing complex calculations and simulations that are not possible with classical computers. Entanglement is also used in quantum cryptography, where it is used to create unbreakable encryption keys that are impossible to intercept or hack. The Einstein-Podolsky-Rosen (EPR) paradox is a thought experiment that was proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. The paradox was designed to challenge the principles of quantum mechanics and their implications for our understanding of the universe. The paradox is based on the concept of entanglement, where two or more particles become linked in such a way that their properties are interdependent, regardless of the distance between them. The paradox suggests that this interdependence violates the principle of locality, which states that physical systems cannot be influenced by events outside of their immediate surroundings. The thought experiment used by Einstein, Podolsky, and Rosen to challenge quantum mechanics involves the entanglement of two particles. The experiment begins by creating two entangled particles, A and B, and then separating them by a large distance. Next, the spin of particle A is measured, and it is found to be up. According to the principles of entanglement, the spin of particle B should be down, regardless of how far apart the particles are. However, this violates the principle of locality because the spin of particle B appears to be influenced by the measurement of particle A, even though they are separated by a large distance. The EPR paradox challenged the principles of quantum mechanics and suggested that the theory may be incomplete. The paradox implied that there must be some hidden variables that determine the properties of particles, even if we cannot observe them directly. However, in 1964, John Bell proposed a theorem that demonstrated that the predictions of quantum mechanics are incompatible with any theory that includes hidden variables. This means that the entanglement observed in quantum mechanics cannot be explained by classical physics and must be accepted as a fundamental property of the universe. The implications of the EPR paradox and the subsequent Bell theorem are profound for our understanding of the universe. They suggest that the universe is not deterministic, and that the properties of particles are fundamentally interconnected in ways that we do not yet fully understand. The Bell inequality is a concept in quantum mechanics that relates to entanglement. It was proposed by physicist John Bell in 1964 and is used to determine if a system is entangled or not. The Bell inequality states that if the properties of entangled particles are correlated more strongly than allowed by classical physics, then the system is entangled. To test the Bell inequality, several experiments have been conducted, including the aspect experiment in 1982 and the CHSH experiment in 1969. The aspect experiment involved measuring the polarization of entangled photons that were separated by a distance of over 25 kilometers. The experiment demonstrated that the correlation between the properties of the photons was stronger than allowed by classical physics, confirming the existence of entanglement. The CHSH experiment involved measuring the correlation between the spin of two entangled particles. The experiment demonstrated that the correlation between the particles was stronger than allowed by classical physics, confirming the existence of entanglement. The Bell inequality has significant implications for our understanding of entanglement and the nature of reality. It demonstrates that entangled particles are fundamentally interconnected in ways that cannot be explained by classical physics. This means that our understanding of the universe may need to be revised to include the principles of quantum mechanics. The Bell inequality also has important implications for the development of quantum computing. Entanglement is a fundamental principle of quantum computing, and the ability to manipulate and control entangled particles is key to the development of quantum algorithms and technologies. The Bell inequality is a key concept in quantum mechanics that demonstrates the existence of entanglement and challenges our understanding of the nature of reality. So, there you have it, folks. We've explored the strange and wondrous world of quantum entanglement, from the mind-boggling EPR paradox to the Bell inequality experiments. It's clear that the more we learn about this phenomenon, the more we realize just how mysterious and fascinating it truly is. But don't worry, we're not done yet. Here at TechNation, we're dedicated to bringing you the latest and greatest insights into the world of science and technology. So, if you've enjoyed this video, be sure to hit that like button, share it with your friends, and subscribe to our channel for more exclusive content. Who knows what other mind-bending concepts we'll be exploring next? The only way to find out is to join us on this exciting journey.